So today I'd like to discuss a topic that I found fairly confusing. I didn't really understand it when it was presented to me in class, and so what I did was I went onto YouTube and then I looked at 5 or 6 videos, and eventually I tried to figure out what this whole lipid metabolism stuff is all about, and I summarized it in one pathway. And I got the details confirmed with my preceptor, and so hopefully all of the following information is scientifically accurate, and obviously a lot of it has been left out, but we're going to concentrate on the basic science that is clinically relevant to lipid metabolism and dyslipidemia. So really made this video to help other people understand lipid metabolism, those people who particularly needed a little bit more clarification, especially like how I did when I was trying to understand this stuff. So lipid metabolism has 2 main pathways, and one is the exogenous pathway, where fats from the outside gets absorbed into the body. And the other one is the endogenous pathway, where the body makes its own fat. And then it circulates around the body, and then it does stuff to the body, and the body does stuff to it. So first we're going to concentrate on the exogenous pathway, and what that means is that when we eat, dietary fats enter the intestine. The intestine packages those fats, like the triglycerides and the cholesterol, into a particle, and that particle is called the chylomicron. And all the particles that I'm going to talk about, I'm going to write in blue. Now it's going to secrete this particle into the lymphatic system. And once it gets into the lymph, it gets associated with an apolipoprotein, B48. Now this chylomicron travels through the lymph, it bypasses the liver, and eventually ends up in the bloodstream. Now once it's in the bloodstream, it's still going to have that B48, and it's going to acquire 2 new apolipoproteins, and the first one is E, and the second one is C2. Now what's going to happen now is that this chylomicron is going to be circulating through the blood, and it's going to encounter fat tissue. Now fat tissue has enzymes such as lipoprotein lipase. What's going to happen here is that the C2 apolipoprotein is going to track this chylomicron to the fat, like so. And what's going to happen is that the lipoprotein lipase is going to take that triglyceride, break down, it's going to take that triglyceride into the fat in the form of free fatty acids, which is what the fat likes to use. Then what we're left with is not very many triglycerides, because it just got taken into the fat. We still have quite a bit of cholesterol, we still have our B48, we still have our E. However, the C2 is no longer present because it was used to track the particle into the fatty tissue and was thus used up in this recognition reaction. Now what we have here is not really a chylomicron, but a chylomicron remnant. Now what's going to happen to this particle is that the apolipoprotein E is going to track it to the liver. It's going to meet with a receptor called LDL receptor at the liver. The liver is then going to take up this chylomicron remnant, and it's going to use the cholesterol to make glucose, apolipoproteins, things like bile, and some hormones. So that essentially is the exogenous pathway. Fats from the exogenous environment come into the body, into the intestine, forms a chylomicron through the lymph, through the blood, delivers the triglycerides into the fatty tissue, becomes a remnant particle. That remnant particle gets taken up into the liver, where that cholesterol can be used to make all the things that the liver needs to make. Now we're going to move on to the endogenous pathway. So the endogenous pathway starts with the liver making its own fat particles. This fat particle has a B100 apolipoprotein. This first fat particle that comes out of the liver is called a VLDL. And when it gets into the blood, now let's pretend it's in the blood, it's going to, just like the chylomicron, it's going to acquire two new apolipoproteins, the E and the C2. And then what's going to happen is that this VLDL is going to move through the blood, and it's going to encounter some fatty tissue, and the C2 is going to track this particle to the fat, where the lipoprotein lipase is going to take the triglyceride from this particle into the fat in the form of free fatty acids, just like what happened to the chylomicron. Now what happens to this particle is now it has very little triglyceride and still quite a bit of cholesterol. Still has that B100 and still has the E, but no longer has the C2, because the C2 was used in the recognition system by LPL. Now, what we have here is not the VLDL, but the VLDL remnant particle. It's also known as the IDL. Now what happens is that the ApoE receptor on the IDL tracks it back to the liver to a receptor called the LDL receptor. Now 50% of the IDL gets taken up into the liver. And then 50% of the IDL gets recognized by the liver, but it doesn't get taken up. It, in fact, forms another particle with some triglyceride and some cholesterol. Still has that B100, Now it doesn't have that E. It doesn't have the E because the E got taken up in the recognition system by the liver, because the E was what tracked the IDL to the liver. So the IDL, half of that absorbed by the liver, half of that became a new particle. This new particle is called the LDL. Now, two things can happen to the LDL. The first is that 80% of it comes back to the liver and gets taken up by the B100 receptor. Gets taken up. 80%. Now, 20% of the LDL goes into the periphery, and some of that is going to be taken up by the macrophages inside the vessels, contributing to atherosclerosis. Now it's important to note here that, let's go back to the IDL. So half of the IDL was absorbed by the liver, and then half of that was then transformed into the LDL. And this transformation occurred via an enzyme called CETP, cholesterol ester transfer protein. And so that is a story of how the liver creates VLDLs, which then deposit its triglyceride into fatty tissue, becoming IDLs. The IDLs, half of that goes back to the liver, and then half of that becomes an LDL. Then the LDL, most of that, 80% of it, gets reabsorbed by the liver, but 20% of it goes to the periphery and gets deposited. And so the larger your initial value of LDL, the larger your 20% is when it gets deposited, and the more atherosclerotic processes you will have. So now that we've talked about how the garbage can be deposited, we need to talk about a process called reverse cholesterol transport, which is achieved by a particle that is released from the intestines as well as the liver. So we'll just use this intestine instead. So the squiggly lines means secretion, and so the liver secretes, and the intestine also secretes this particle with an A1 apolipoprotein, and this particular particle is called the high-density lipoprotein. And this is the so-called garbage truck that takes out the garbage. And so what this thing does is that it's going to go to the periphery and it's going to pick up this cholesterol. So you see how this HDL is empty at the moment. It's going to pick up a whole bunch of cholesterol. and then this cholesterol, and then this HDL is going to interact with this LDL. And what it's going to do is it's going to give the cholesterol to the LDL. And the LDL is going to give triglyceride to the HDL. This reaction is catalyzed by CETP. So the cholesterol that the HDL picks up from the vessels goes to an LDL. The LDL gives the HDL triglyceride. Now, the cholesterol from the HDL comes to the LDL, and then what happens there is that 80% of the LDLs are going to be taken up by the liver, and 20% are going to be deposited. But then, the HDL is going to come to the vessel and pick it back up again, and then give it to an LDL. The LDL is going to bring it back to the liver. Now, that is one of the three things that can happen to an HDL. Now, once it has picked up all of the cholesterol, I'm just going to draw the exact same thing up here. So this is a cholesterol-rich HDL. It is then going to go to certain peripheral tissues, such as the liver, such as the testes, and the ovaries, and the adrenal medulla, and it's actually going to deposit this cholesterol into these organs for these organs to make their hormones. And it's going to deposit the cholesterol through a receptor called the SRB1 receptor. Now, once it has finished dumping the cholesterol in there, it is then going to be emptied of cholesterol. And it's going to be cholesterol poor HDL, which is the same thing that was originally secreted by the intestine and by the liver. And then this cholesterol poor HDL can then go to the vessels to pick up more cholesterol. Now, there is a third thing which can happen to an HDL, and what happens there is that the periphery, so the peripheral tissues, can in fact give more cholesterol to the HDL. And this happens through SRB1 receptors again, as well as this ABCA1 receptor. So this HDL is now enriched in cholesterol from the periphery, and as you can see, this HDL is the same as this HDL is the same as this HDL, and so once it's picked up cholesterol from the periphery, well, it can give it to LDL, which then goes back to the liver, and some of it goes into the vessels. This thing can deposit that cholesterol into the organs and then become cholesterol poor. So there's a variety of possibilities for this. And so really the thing to know here is that the HDL is responsible for reverse cholesterol transport. It is characterized by apolipoprotein A1, secreted from the intestine, secreted from the liver. There are three things that can happen to this HDL. And the first thing is that it can go into the vessels and pick up the cholesterol to become cholesterol-rich HDL. And then this cholesterol-rich HDL gives cholesterol to an LDL, which 80% of it goes back into the liver, and then 20% goes into the vessels. That is the first fate of this HDL. The second fate is that it can go to the periphery to pick up the cholesterol and now becomes cholesterol-rich. And this particle is exactly the same as this particle just drawn up here, and now it can dump this cholesterol into the organs that need to make hormones, and then after it's dumped the cholesterol, it's emptied of cholesterol and it goes back here. That was the second fate. Now the third fate of this HDL is, well, it can pick up some of the peripheral tissue cholesterol. It can pick up the cholesterol from the vessels, become rich, and then go to the periphery and pick up even more cholesterol. And now that it has a lot more cholesterol, well, this particle is the same as that one. This can give the cholesterol to LDL, and 80% goes into the liver and 20% goes into the vessels. Or once it's cholesterol rich, it can be dumping the cholesterol into the organs that need it and becoming cholesterol poor again. So that really is the system of reverse cholesterol transport, and how the HDL takes the LDL, the atherogenic LDL particles and the cholesterol from the vessels and takes it back into the liver via the LDL. And so before I finish off here, just going to talk about a few quick notes on the players of this system that can cause disease. And the first first area that we want to look at is the exogenous pathway. So exogenous pathway makes chylomicrons, goes in the blood, gets a bunch of apolipoproteins. And so what happens here is that if the ApoC2 is deficient, okay, that means that this particle will not go to the fat, it will not be hydrolyzed into a chylomicron remnant. So if it doesn't undergo this reaction, this entire particle is going to build up in the blood. And this is going to lead to chylomicronemia syndrome. ApoC2 deficiency leads to chylomicronemia syndrome. Okay, so now let's look at the endogenous pathway. Remember, that was where the liver made its own VLDL, etc. And so, okay. So when we look at the VLDL, it has a bunch of apolipoproteins, and one of them is the apolipoprotein E, and it is the one that brings it back to the liver for this IDL to be reabsorbed. Now, if we look at the apolipoprotein E, there is a certain isoform called the E2, where it is somewhat defective. And so if you have increased ApoE2, it actually reduces the recognition by the LDL receptor, and so you have reduced ability for this particle to be tracked to the LDL receptor and subsequently be taken up by the liver. And so what that results in is you have very high levels of IDL, and the result of that is what we call familial dysbeta-lipidemia. So in short form. Now, we know that, now the third thing is that when the endogenous pathway, where it makes the VLDL, well, obviously to make a VLDL, you need to have beta apolipoproteins. And so if you have a reduced, a primary reduced apoprotein B, then you are not going to be able to make the VLDL, and that is a syndrome described as hypo-beta-lipidemia. And that actually reduces your cardiovascular risk. However, it can cause malabsorption and neural defects in an infant. Now, the next thing to look at here is that the LDL is taken up by a B100R receptor, which is a subset of the LDL receptor. And so if the ApoB is defected, or if the receptor is defected, the LDL cannot be taken back up into the liver. And this results in very high levels of LDL. And what that is called is something called a familial hypercholesterolemia. And this happens at that level. So first we discussed a chylomicronemia syndrome, where the C2 apolipoprotein is defective. You can have reduced levels of ApoB, and so therefore reducing your ability to make the VLDL, and thus reducing the IDLs and the LDLs in the circulation, and thus actually improving your cardiovascular risk. You can have different isoforms of ApoE lipoprotein, which means that it is not as absorbable by the liver, and so what happens there is you have a familial beta-lipoproteinemia characterized by very high triglycerides, because as you remember, never mind about that. That wasn't the point. And then the last thing is familial hypercholesterolemia, where you have either an apolipoprotein B defect here, or you have an LDL receptor defect here. It doesn't get taken up. You have a lot of LDL hanging around, and then you get familial hypercholesterolemia. And the last thing to note is that sometimes you can get a primary reduction of HDL, and that's just called reduction of HDL. There are various genetic causes of that, and what that really means is, well, you're going to have a reduction in reverse cholesterol transport, and so you're not going to have this HDL, so you're not going to collect the lipids from the vessels, you're not going to collect the cholesterol from the periphery, and, well, you're not really going to have cholesterol going into the organs that you need to make hormones. But the main thing is it's going to increase your